Have you ever really stopped to think about what happens when you type a command into your terminal and hit enter? I mean, it feels instant, right? But underneath the hood, especially on systems like Linux or Mac OS, the process is, well, it's kind of wild. Today, we're going to unpack a design that is both totally bizarre and absolutely brilliant. And I promise, once you get it, you'll never look at your computer the same way again.
So let's start with a really basic question. You want to run a new program. How does the computer do it? The obvious answer, the one that just makes sense, is that the operating system finds the program on your disk, loads it up, and runs it. Simple, A to B. Done, right? Well, the pioneers of Unix didn't go for the obvious answer. They took this incredibly winding, indirect path. At first glance, it looks just needlessly complicated. But buried inside that complexity is a secret, a kind of hidden genius that we're going to unravel together. And here is where things get really weird. To run a new program, the very first thing a Unix system does is make a nearly perfect copy of the program that's already running. I'm serious. Think about your command line shell. To run a simple command like ls to list files, it first makes a complete identical clone of itself. It's like wanting to bake a cake and starting by building a perfect replica of your entire kitchen. It makes no sense. Or does it?
This right here is the central mystery. Why on earth would this be the first step? It seems so wasteful, so backwards, but stick with me, because the answer to this question is a genuine stroke of genius that has shaped how we build software for over 50 years.
Okay, so to understand this, we need to meet the first piece of the puzzle. It's a system call with a deceptively simple name, fork, and you can think of it as the operating system's cloning machine. So what does it do? When an existing process, we'll call it the parent, calls fork, the operating system stops everything and creates a brand new process, the child, that is an almost exact duplicate. It has its own memory, its own state, but critically, it's running the exact same code as the parent.
Now here's the part that really bends your brain the first time you hear it. Imagine a single line of code in your program, RC equals fork. Before that line runs, there is one process. The instant that line finishes, there are two. The new child process doesn't start from the beginning of main. No, it just materializes into existence right after the fork call as if it had been there all along. From that moment forward, you have two processes, parent and child, both about to execute the very next instruction.
So you're probably wondering, if they're both running the exact same code, how do they know which one is the parent and which is the child? This is the clever part. The fork call returns a different value in each process. In the parent, it returns the process ID, or PID, of the new child it just created. But in the child, fork returns 0. This one tiny difference is everything. It lets us write a simple if statement to give the parent and child completely different jobs to do.
But here's a new problem. Now that we have two totally independent processes, who runs first, the parent or the child? Well, the answer is, you don't know. It's up to the operating system's CPU scheduler. It might let the parent run for a bit, then the child, or the other way around. This is what we call non-determinism, and it means the output of our little program is totally unpredictable. It's a race, and we have no idea who's going to win.
Now, this kind of unpredictability is usually a disaster for programmers. We need control. What if the parent actually needs something from the child before it can move on? How do we tame this chaos and bring some order back to our system?
And that, of course, brings us to the second system call in our toolkit, wait. This is the function that lets us put the parent on a leash and get our processes back in sync.
The wait system call does exactly what it sounds like. When a parent process calls wait, the operating system basically puts it to sleep. The parent process just pauses. It won't wake up, it won't do anything until one of its children has completely finished its work and exited. So check this out. In our code, in the part that only the parent runs, we just add a call to wait. That's it. This one line acts like a giant pause button for the parent. It's telling the OS, hey, I'm just going to chill here. Wake me up when my kid is done.
And just like that, the chaos is gone. The output is now 100% predictable. Because even if the scheduler tries to run the parent first, the parent will immediately hit that wait call and go to sleep. This gives the child a chance to run, do its thing, print its message, and exit. Only then does the parent wake up and continue. Order is restored.
Okay, so we're making progress. We can make a clone and we can wait for it. But we still haven't answered the big question. How do you run a different program?
And that is the job of the third and final piece of our puzzle, the execf family of system calls.
Get ready for another mind-bender. Exec does not create a new process. What it does is, it transforms the process that calls it. The operating system essentially takes the code for the new program and overwrites the current process with it. The old program is completely wiped out and replaced. And here's the kicker. A successful exec call never ever returns. Why? Because the program that made the call doesn't exist anymore.
So let's put it all together. The parent calls fork, now we have a child clone. Inside the child's code, instead of just printing something, it calls exec and tells it to run, say, the word count program. The moment exec is called, that child process undergoes a metamorphosis. It stops being a clone of our original program and becomes the word count program, starting from its own main function. So now we have all the pieces. Fork, clones, wait, synchronizes, and exec transforms. We can finally go back and answer that big question from the beginning. Why separate all these steps? Why not just have one single command like spawndet that does everything at once?
This quote from the legendary computer scientist Butler Lamson just nails it. The Unix designers could have made a simpler, more abstract API, but they didn't. They chose this approach because it was the right one, and the reason it's right is because it's unbelievably powerful. The entire secret, the magic, it all lies in the gap. That tiny window of time in the child process after it's been forked, but before it calls execute. In that moment, the child is a clone of the shell, and it can mess with its own plumbing. For example, if you want to redirect output to a file, the child can simply close its connection to the screen, open a file instead, and then call execute. The new program that starts up has no idea what happened. It just starts writing, and its output magically goes to the file.
And that's the whole shebang. That's the genius of it. This separation gives a normal, everyday program, the shell, the power to set up the world perfectly for another program before it even begins. This is how I/O redirection with a little greater than arrow works. It's how pipes work. It's not some special magic in the operating system kernel. It's all happening right there in user space thanks to this beautiful, elegant design.
And look, this isn't just some dusty old academic topic. Understanding this why, the philosophy behind the design, is a cornerstone of computer science fundamentals, and it's something that comes up constantly in high-level technical interviews.
So let's just game this out. You're in a big tech interview for a senior systems role, and the interviewer leans forward and asks you this exact question. After what we've just gone through, you're ready to absolutely nail it.
Here's how you knock it out of the park. You break it down into 3 points. Number 1, flexibility. That gap between fork and X is a feature, not a bug. It allows the shell to meticulously set up the child's environment. Number 2, simplicity. It follows the core Unix philosophy of having small tools that each do one thing and do it really well. And number 3, power. It delegates immense power, like setting up pipes and redirection, from the kernel to regular user programs, making the whole system more modular and robust.
Ultimately, the fork and exec model is just a beautiful reminder that sometimes the most elegant and powerful solution isn't the most direct or obvious one. It makes you wonder, right? What other designs that we use every single day seem a little strange on the surface, but are actually hiding their own secret layer of brilliance? Thanks for joining me.